Hi guys, it is Mr. Woodward again, and today we are going to work on our 3-bit adder. So I want to do, well, I guess first let's go over our objective for the day, just so we all know what the targets are. So I want you to be able to identify inputs and outputs for our 3-bit adder. I want you to know which gates correspond to addition, multiplication, and an inverse. I want you to know that K-maps help to simplify equations. And I want you to recognize that truth tables and K-maps show the same thing, just in different ways, and they kind of have a different purpose. I want you to understand that there are multiple correct solutions for this problem and really for most engineering problems. You get to decide which correct solution is the best one, and you get to be creative with that. And finally, I want you to be able to transfer data from a truth table to a K-map. I want you to use 4 input K-maps to create equations. And I want you to use those equations to create a 4 input, 3 output circuit in Circuitverse. So let's go ahead and get started. And we're going to review binary just really quickly because we are going to be adding in binary today. So I think it's important to know what our binary numbers mean. And you'll notice that I've written all these binary numbers out as 3 digits. And that's just to be, I guess, complete. Because notice for 7, which is 111 in binary, I have to use all 3 digits. So for 0, even though I could just say 0 in binary, I want to say 0, 0, 0, just to be consistent all throughout. So here's just a quick little reminder of how we viewed binary in the past, that ripple through method. So there's 4, 5, 6, 7, 8, and then back to 1. And then another cool thing that I just found today is a more mechanical version of what we're going to be building today. This is a representation of what's actually happening in a computer or a calculator, I guess, when you're asked to add things or when you ask your calculator to add things. And you can see those little flip-flops going back and forth. And you can think of those going back and forth as moving from 0 to 1. And you can see how that information can ripple through. That's why we call it our ripple method. So here is the problem that we are trying to solve. We want to take 2 numbers that each have 2 digits in them, and we want to be able to add them together. So we have our green number on top, represented by AB, and we have our purple number on bottom, represented by CD, and they will add together to produce a 3-digit output, X, Y, Z. So let's go through this truth table real quick. 0, 0 in the green plus 0, 0 in the purple. Well, that's 0 plus 0. It adds up to be 0. 0, 0 plus 0, 1 is going to add up to be 0, 0, 1. 0, 0 in green plus 1, 0 in purple is going to be 0, 1, 0. And our last one, I bet you can figure out because AB is 0, 0. Now, for our next set of 4, notice that AB will be 0, 1. So it's going to be 1 plus something every time. So now it's 1 plus 0, so that'll be 1. 1 plus 1 is going to be 2, or in binary, 1, 0. 1 plus 2 is going to be 3, or in binary, 0, 1, 1. And then finally, 1 plus 3, so that's 0, 1 plus 1, 1, is going to be 1, 0, 0. Moving on, 1, 0 plus 0, 0 is 0, 1, 0. 1, 0 plus 0, 1 is 0, 1, 1. 1, 0 plus 1, 0, that's 2 plus 2, is 1, 0, 0. 1, 0 plus 1, 1 is 1, 0, 1. 1, 1 plus 0, 0 is 0, 1, 1. 1, 1 plus 0, 1, so that's 3 plus 1 is going to be 4, 1, 0, 0. 1, 1 plus 1, 0 is going to be 1, 0, 1. And finally, 1, 1 plus 1, 1, so that's going to be 3, plus 3 equals 6, or in binary, 110. So that was just a whole bunch of stuff. So if you need to pause and work through on your project notebook, now would be a great time to do so. But I'm going to just keep moving. Again, feel free to pause and move back through and watch this video as many times as you need to. But really quickly, let's review how to get an equation out of a truth table. So the easiest way to do this, and I'm looking for x right now, is I would find all of the places where x is equal to 1. And they're right there. And all those places where x is equal to 1, I want to look at the inputs, and that will give me a piece of the equation. So our first one, for example, right here, 0, 1, 1, 1. So that would be not A, because A is 0. And then it would be B, C, D. Or, and remember we represent or by that plus sign, or 1, 0, 1, 0, so that'll be A, not B, C, not D, or 1, 0, 1, 1, which is A, not B, C, D, or A, B, not C, D, or A, B, C, not D, or A, B, C, D. And that can be difficult and overwhelming if you're new to it. And of course, you guys are. You're an introduction to engineering. So we have introduced something called a K-map, and it'll help us simplify these equations. So really quickly, let's review K-maps and just how to use them. How do you actually go from a truth table to a K-map? So this is difficult to explain over the computer. But I'm going to do my best, and I use some color coding here to kind of show you which spot on a truth table will map to a spot on a K-map. And all the numbers on the K-map there represent which row that I'm talking about when I'm talking about X. So important to note is when we're using a K-map, we will always skip the third. Okay, remember, because we are writing in grayscale, not grayscale, that's from Game of Thrones, because we are writing in gray code, we'll always skip the third. So we go 0, 0, 0, 1, 1, 1, 1, 0. So if you see in that first column of my K-map, it goes 1, 2, 4, 3. So take care to always skip the third there. For our 5th, 6th, 7th, and 8th row, you see it's right there. And again, our colors line up. And again, we skip the third. We're now going to skip that entire third column for our 9th, 10th, 11th, and 12th entries. And again, recognize we are still going to flip the third. And then we'll wrap up here in our third column with 13, 14, 15, and 16. So I'm going to magically input all of this stuff into a K-map. But I would like for you guys, before you move on in this video, to attempt to do this yourself. Let's see if you can figure out what the K-map for X looks like. Okay, waiting, and I'm going to move on. Hopefully you got this right. Now, remember, the whole point of a K-map is that we can circle our ones, and they produce a simplified equation for us. And remember our rules. You're allowed to circle 1, 1, 2 ones, 4 ones, 8 ones, and so on and so on and so on. I think this one is the most manageable K-map of the three. And so I'm going to leave this as an exercise for you guys. I believe that you can solve this one on your own. And I'm going to move on to Y. So here is our completed K-map for Y. And if you're looking at this, you might be thinking to yourself, uh-oh. And I would agree with you. This is by far the trickiest K-map that we have worked with. Because remember, you're not allowed to circle on a diagonal. You are not allowed to circle any zeros. So we're pretty limited with what we're able to do. we're able to circle right there. That's a group of 2. So we're able to eliminate one variable. And I'm going to leave it to you to figure out which variable we eliminated. I'm going to give you about 5 seconds. Well, when we look in that column, we notice that the red circle stays in that column the whole time. So we know that not A, not B will be part of our equation. When we look at the rows, that red circle goes from the 3rd row to the 4th row. And you can see that C stays the same. It's 1 in the 3rd row and it's 1 in the 4th row. But D changes. D goes from 1 to 0. So we will not include D. That's the variable that we are actually able to eliminate. Our next circle, that blue circle right there, stays in the same row. It's in that 4th row. So we know that C1, D is equal to 0. So that'd be C not D. We know that both of those are going to be included. But what variable gets removed in that situation? And hopefully you would say that B does, because B moves from 0 to 1, where A stays the same, which means that our second circle is represented by not A, C, not D. Similar thought up here. It stays in that first row, not C, not D. A stays the same as a 1. B changes going from 1 to 0. So we would have A, not C, not D. Here we stay in the same column, so we'll have A, not B, and then D changes from 0 to 1. C stays the same, so we'll have our A, not B, not C. Lastly, we have those 2 guys in the middle, and there's nothing to do about them. We don't get to eliminate anything, which is a real bummer. So it just stays what it is. It is 0, 1, 0, 1. So that means it's not A, B, not C, D. Same for our last circle there. It's A, B, C, D. Now that is what our K-map will give to us. And that is a simplified version. Kind of surprising that that's simplified because it still looks really big and really nasty. I will say that I worked on this some last year and I was able to simplify it further. But that is a correct equation for you to move forward with. Lastly, we want to work on the K-map for output Z. Now, when you look at this at first glance, you're probably thinking you will make 4 circles and it'll look like that. And that is true, that will work. That won't be the most simple way to do it, though. And there's a trick that I haven't talked to you guys about yet in class. We went over it very, very briefly. But if you picture our K-map like the label to a can of soup. So if you kind of picture this GIF working in reverse, you can see how the 2 edges of those rectangles actually touch, which means those ones on the very outside actually touch. So you can circle them as a group of 4 like that. And I understand that that is weird for you. But just keep playing our game. You'll see as we move from our second column to our third column, A changes. A goes from 0 to 1, where B stays the same. It stays as a 1. And if we look at our first row and our fourth row, which are actually connected, we'll see that C changes. It goes from 0 to 1, whereas D stays the same. It stays as a 0. So that means we get B, not D. We can do a similar trick and circle right here. But I'm going to leave that last piece as an exercise for you. So really quickly, to review, we went through the truth table for a 3-bit adder. That means we have a calculator that does addition, and the output will always have 3 digits. So we did the truth table for that. We produced K-maps for each of our 3 outputs. I'm going to leave it to you to figure out the simplified equation for X. I gave you a simplified equation for Y, and we went through and did half of the simplified equation for Z. And I believe in your ability to get the other half of that equation. So in conclusion, you should feel pretty confident working through this objective. You should be able to identify the inputs and outputs, which is just A, B, C, D, X, Y, and Z. You should be able to know which gates correspond to addition, multiplication, and not. You should be comfortable working with K-maps and truth tables. And you should understand that there are multiple ways to get this done. And that's part of the creativity of being an engineer, is being able to figure out which correct answer works best for you. So finally, you should have been able to produce your 3 equations. And in our next video, we'll talk about how those 3 equations can produce 3 different circuits. And really, it's going to be one larger circuit that has 4 inputs and 3 outputs. And we're going to be building that in Circuitverse. So good luck.